Okay, welcome to CULINOLOGY101. Okay, this is for week 9. Today's the title will be forming solution. Okay, let's look at the learning objective. First is to predict in a general way the solubility of solutes in solvents on the basis of molecular polarity. Okay, able to calculate the solution concentration in units of molarity, weights per weights percent or weights per volume percent. Okay, describe the formation process of solutions. Okay, how the solution is formed. Do the calculation using the concept of the self-ionization of water and the pH concept. Explain the difference between strong and weak as applied to acid and bases. Okay, so all these informations are knowledge, not information. These knowledge are very fundamental here. Okay, you will be using it all the time for product development. So you make sure that all this foundation you are strong enough. Okay. Okay, let's look at this. The first one, introduction to solutions. Okay, what is solution? Solutions are homogeneous mixture of two or more substances. Okay, it can be atoms, molecules, or ions. Homogeneous means that they are together. Okay, heterogeneous means they are not together. Homogeneous they are together. And they are more or less compatible with each others. Okay, so solution are homogeneous mixture of two or more substances. They are transparent. Most of the times they are transparent because these uniformly distributed particles, either a small molecule or ions, are too small, less than about 0.1 micrometer in diameter, to reflect light. So when you want a certain color, especially like for example like milk, the particle, the droplets of the oil droplets are large enough. So what happens is that the light, when you pass through, it will reflect. Okay, so it reflects. So what happens is that reflect. Okay, so when you look at it, right, it's white in color because the light cannot pass directly into your eyes. Okay, for solutions, again, depending on what kind of ingredients you put inside. In general, solutions are made of the small molecules. Yeah, can be molecule, atoms, iron, and so forth, and they are usually very small to actually reflect light, so they are transparent. But if you are looking at using something bigger like proteins, again, depending on the concentration as well, probably you might get some reflection of light and you may not see a transparent solution. Yeah, all right. For transparent solution as well, you may say that, sir, how come some they are not really like transparent? Because they put color molecule. Color molecules, they absorb light. That's why they look, they have a certain color. Okay. So there are a lot of products in the markets. They are considered as solutions. You can see from here all type of beverages. When you're looking at the solution, there are two main components here. You can actually assign, okay, two of these. You can assign one liquid is considered as solvent, another one is called solute. Solvent is the substance present in the solution in the largest amount. Okay, what happens is that the solvent will be the one that dissolve the solute. Solute is one or more substance present in the solution in amount less than that of solvents. Yeah, okay. So you can see over here, the solutes, you can actually have a few, not just one, a few solutes that actually dissolve in the solvent. Alright. So some of the examples, for example, salt water. When you're looking at salt water, the solvent will be water. The solute will be the sodium chloride. Okay. Okay. When you're looking at the alcoholic beverages, the solvent is water. The solute will be alcohol. Yeah. For carbonated water, the solvent will be water. The solute will be carbon dioxide that is being pressurized and dissolved in the water. Okay. The second part will be looking at the solubility of solute in solvent. What is solubility? Soluble or insoluble? Soluble is when a solute is a substance that dissolves to a significant extent in a solvent. Okay, so there's a line over here. Okay, which means that it needs to dissolve to a significant extent. Okay, to be have a quite high in the percentage that is being dissolved. Okay, when you're looking at insoluble solutes, it's a substance that does not dissolve to a significant extent in a solvent. So when you're looking at this, a sugar can be dissolved quite well in the water. Okay, in this case, you can see that if you add 1 gram of sugar into water, when after you stirring it, it completely dissolved in water. Okay, so this is what we call the sugar is soluble in water. Whereas if you're looking at the oil and water, they are not compatible with each other. Okay, as you have learned from organic chemistry. Okay, because the water is polar, the oil is non-polar molecule. Okay, so what happened, right, is that it cannot be dissolved and hence is insoluble. The oil is insoluble in water. Whereas alcoholic, the alcohol, for example, ethanol, right? If you add 10 drops of ethanol into water, it can dissolve completely. So what you call is soluble. So the solubility depends on the type of solvent. Okay, as mentioned right before, the polar solvents will dissolve polar or ionic solutes. Very important. In organic chemistry, we have already learned what is a polar molecule. Okay, what is an ionic solute. Okay, when you're looking at the non-polar solvent, it will dissolve non-polar or non-ionic solutes. Yeah. Alright, so polar with polar, non-polar with non-polar. Always remember that, okay? Okay, polar doesn't dissolve non-polar, or non-polar doesn't dissolve polar. So solubility is definition is the maximum amount of solute that can be dissolved in a specific amount of solvent under specific condition of temperature and pressure. The solubility, alright, of a certain substance, it actually can be affected. Initially, it could be like, for example, 100% soluble. But as you change the temperature or pressure, you actually may decrease, okay, the solubility. Alright, so it really depending on the temperature and the pressure. That's why when you quoting a solubility of a certain substance into a solvent, okay, you need to actually specify the condition, the temperature and the pressure in there, okay. Very important. Always specify. Okay, for example, when you're looking at this, alright, even though it's soluble, although you can be categorized as significant amount of solute dissolved in the solvent, but each of the substance, they have a specific solubility. So you need to check with that as well, because if you go more than that, beyond the amount that you put into the solvent, then it cannot be dissolved anymore. Yeah. So it's in the case, for example, the ascorbic acid. Okay, so the solubility is 33 grams of ascorbic acid in 100 grams of water. Okay, that's quite a lot actually, 33 grams. Okay, in 100 grams of water. Yeah. Then you can see sucrose, okay, which is the table sugar. It's about 179.2. Alright. Then all this is almost infinite, yeah. Okay, but of course, if you go until beyond certain concentration, then this substance will become a solvent already, not solid. So what if exceed the maximum limit? Okay, the one that I told you before. Like for example, a gram of sugar, if it dissolve in homogeneous solution. But if you add 300 grams of sugar, what will happen to it? The excess sugar will not be dissolved. How you explain this is because each of the molecule of the sugar molecule will interact with a water molecule. Okay, will interact with water molecule. When the amount of sugars exceeded the amount of water molecule available to interact, then of course, obviously, the sugar cannot be dissolved anymore. Alright, and in this concentration, we'll call it as a saturated solution. Okay, saturated. Of course, this saturation can be adjusted using temperature and also pressure. Okay, usually if you increase the temperature, okay, when you increase the temperature, you can actually dissolve more. As soon as the temperature cools down, that actually those that dissolve will start to come out from the solution. Okay. For example, when you're looking at this, you can see sucrose. All right. So at room temperature, which is about 24, 25, is about 11819 grams per 100 grams of water. As you increase the temperature, what happens? You actually can dissolve more. Okay, but you have to be extra careful. You say that, oh, since it's in that way, I just heat up and again I can get more sugar into the solution. But one thing is that, remember this, how long can you maintain the temperature at that high temperature? As soon as the temperature drops back to room temperature, what happens to the sugar, table sugar? It will come back out to the liquid. Okay, it will come back out from the solution. Okay, which means that it becomes saturated again, and the amount there will be a significant amount of sugars will be not dissolved in the solvent. Okay, so you can see some of the items. Okay. But one thing you can see from here, for gas, okay, usually gas in this way, as you increase the temperature, the solubility of gas will decrease. Okay, very important. Yeah, that is gas. All right, that also ties very well to the next one we're going to talk about, which is the carbonated soft drink, where we actually press the carbon dioxide into the solution. Okay. So carbonated is CO2 into the solutions. Actually, it dissolves more at colder temperature. Okay, so when the temperature went up, okay, it dissolves less. What is the impact? I will explain to you soon. Okay, so what happened? Why is it the soft drink best served chilled? Why is it like cold is always the best? Okay. When it's warm, something is missing. Okay, if you realize the tingling or the sensation, okay, from the release of the carbonation is different if you drink the soft drink warm or room temperature versus cold. You will realize that if you drink the soft drink at cold temperature, you actually feel more fuzziness. Okay, and of course you will burp louder as well. Okay, because when you drink, all right, what happens is that the higher, the colder the temperature, it actually can dissolve more carbon dioxide in the solvent. Okay, so which means that when you drink, there's a maximum amount, there's a high amount of carbon dioxide in the soft drink. When you drink, when it reaches to your throat or your stomach, okay, then the CO2, because of warmer body temperature, it will release out. That's why you burp. That's why you feel the fuzziness in your throat. Alright. Whereas if you drink it at room temperature, what happens is that as soon as you open up, okay, the gas will start to release out into the air. So when you drink, of course, it's less carbon dioxide in your body. Okay, it's less carbon dioxide will enter into your throat or into your body. So what's the effect of pressure on solutes and solubilities? If you are talking about liquid and solid solutes, pressure has minimal effect. For gas, the pressure has direct proportion to the solubility. The higher the pressure, they actually can dissolve more solute. That is why for making a carbonated drinks, you need to have a very high pressure to press the carbon dioxide into the liquid. Okay, of course, the carbon dioxide, it won't be in the form of CO2 in the liquid. It will be in the carbonated acid form. Okay. Okay, third is solution forming process. Okay, how the solutions is being formed. Let's look at the molecular structure. When you're looking at ionic compound dissolve, what happens is that the ionic is usually in the orderly form. When you're trying to dissolve, the water molecule, the positive, delta positive part of the hydrogen, okay, will interact or leave out with the chlorine, okay, with the negative charge chlorine, and then the negatively charged, the oxygen, okay, delta negative, slightly negative oxygen will interact with the sodium ion, and one by one it will lifted off from the solute. When you how you're going to speed up? There's a few ways you're going to speed up is by crushing the solutes into smaller. So when you crush it, actually you promote the interaction between the solute with the solvent because more surface area. Another thing is that you can do heating as well. Okay, heating provides the heat actually is the energy. The energy provides the kinetic energy into the molecule. The molecule vibrates more. It actually move faster, and it collides with the solutes at higher temperature. That's why it can interact. Actually, you speed up the thing. Okay. Another thing is through stirring and agitation. That's why when you're looking at factory, usually they have a big stirrer, okay, to stir it, to promote the forming the solutions. Yeah. When you try to form a solution, sometimes you will realize that, hey, how come the solution after it formed, how come it's cold? Sometimes you say, hey, how come it's warm? Okay. So usually when you form a solution, sometimes you may experience an endothermic or exothermic reaction. Yeah. Endothermic is when they absorb heat. When they absorb heat, what happens? You feel cold because the heat is being removed. Whereas it's for the exothermics, when you touch the glass, you feel that, hey, how come it's warmer? Because this, the formation of the solution gives heat. That's why it is warmer, okay, when you touch the beaker. Alright. So the next time when you feel this, you can say that, okay, it can be due to endothermic or exothermic reactions. Yeah. Okay. But one thing, yeah, be extra careful. Yeah, if you have alcohol, okay, when you touches your skin, okay, when you feel cool, that is not due to endothermic. Yeah, it's because the alcohol evaporate, bringing your the heat from your skin away from your skin. That's why you feel the cooling sensation. Yeah. Number 4 is looking at the solution concentration, how to calculate it. Alright. There are certain things here. Concentration is very important. This one definitely will be exam. Okay. Will be in the exam, yeah, your final exam. Please make sure you know how to calculate. Okay, concentration is the relationship between the amount of solute and the specific amount of solution in which it is contained. Concentration is very important. How you actually determine the concentrations, you must actually write down properly the units. Okay, the reason, right, is because the formulation depending on the concentration. Alright, if you change a bit of concentration, your formulation may go away, okay, may not be successful. That's why a proper recording, you want to be in a molarity form, okay, you want to be in weight percentage or weight and volume percentage and so forth. You need to fix one term, okay, fix one type, okay, that is easier, or the what you practices in your company or in your lab, okay, so just stick to one, okay. So what is molarity? Molarity, okay, or what we can use the symbol M, is the moles of solutes divided by the liter of solutions here. Alright, moles of solutes, you already know how to how you calculate, okay, moles, okay. You need to have the molar mass, okay, you can calculate the moles through the molar mass, yeah. How about weight percent? Weight percent is where the weight of solutes in kg, okay, it can be kg or gram, doesn't matter, as long as this two is the same, that's fine, yeah. Weight of solutes divided by the weight of solution. Okay, make sure, yeah, the weight of total solution, yeah, total solution. So which means that is solute plus solvent, the total, the final weight of the solution, which is in combination of the solute and the solvent. Okay, so weight of solute divided by the weight of solvent times 100%. Yeah, this is what we call weight percent. So you can look at here, express the content of the following solution in terms of molarity. Alright, 315 ml of solution contains 10.3 grams of isopropyl alcohol. Okay, this is the formula. Okay, so how you can do this, right, is to find out the the molar mass. Okay, so from the you can see from, so first you must know what is the molar mass of the isopropyl alcohol, so you can calculate from here. So for here is the molar mass is 60.1 grams per mole. Okay, so you're using that, and with the amount of isopropyl alcohol 10.3 grams, so you can, this one divided by the molar mass, you will get 0.171 mole of alcohol. Okay, so from that, to calculate the molar mass, when you have the mole, is to divide the total solution, the volume. In this case, this is in ml, so you convert to liter. Alright, so once you have all the units correct, moles and liters, then you divide, you get 0.543 molar. Okay, and this one, a solution contains 100 grams of water and 1.2 grams of solutes. What is the percent weight to weight concentration? Weight to weight, yeah. Alright, so from here, you know the solution concentration, solution weight is 100 grams. Okay, for here the 1.2 gram of solute, so it's 1.2 gram of solutes divided by the solution weight, which is 100 grams plus 1.2 grams of solutes here. So it will be 1.2 grams divided by 101.2 grams at 100%. Yeah. Alright. So a lot of people, they actually forget this one. They, instead of putting 101.2 grams of the solution mass, they actually put 100 grams of water. Alright. Sometimes you may think that it's not significant, but when the volume is high enough, what happens? It will have a very significant difference. Okay, so make sure you don't mix it up. Yeah. Okay, that's why calculation, all this calculation, you need to make sure that you understand how to do it properly. Alright, if you do it wrongly, what happens is that all your formulation will be wrong. Yeah, when you try to pass it on to your colleague, then when they do it, when they use it, they actually added less. Okay, then they're in big trouble already. Formulation went off already. Okay, describe how will you prepare the following solution from pure solutes and water. Okay, so how do you prepare the following solution? So 1 liter of 1.5 molar of COCl2 solution. Okay, so how you prepare is that first you know the molarity. Alright, find out how many moles or how many grams of the COCl2 solution. So you can, from here, you can find out how many moles are there. From here, how many moles, because it's 1 liter, is very easy to calculate how many moles. From here, how many moles, then you can use the molar mass, okay, and calculate the mass of the COCl2. So it's 195 grams of COCl2. So what you do is that you will add, okay, weigh out 195 grams of COCl2, dissolve with about maybe about 500 ml or half a liter of water first. Okay, once dissolved, alright, then you will put it into the volumetric flask. Okay, and top it up to 1 liter, because the final concentration is 1 liter. Yeah, so volumetric flask is a good way of doing it. So the wrong way of doing it, a lot of people did that, yeah, is to put this 195 gram of COCl2 directly into 1 liter of water. Okay, that is wrong, because you need to remember that the COCl2, especially 195 grams, it actually take up some volume. Because of that, you cannot, if the final volume is 1 liter, you cannot add into 1 liter of water. You need to take in consideration that COCl2 has volume as well. Okay, make sure you understand that. Yeah. Okay, this one very important. Yeah. Okay, make sure you know how to calculate this. Okay, weights per volume. When you're talking about weights per volume, you're talking about a volume of 100 ml. Okay, so if you're talking about 5% of weight per volume solution of KCl, what does it mean? Okay, which means that if you're looking at 100 ml, you got 5 grams of KCl. Yeah, so very simple. 100 times 5%, you get actually 5 grams. Yeah, okay, which means that there's 5 grams in every 100 ml of solution. Okay, so you pick out a 100 ml solution. Okay, inside got 5 grams of KCl. Okay, so this is some of the summary, okay, of different type of weights. So make sure you know how to calculate, because if in the exam ask you to calculate weights per volume, make sure you know how to calculate. If you ask you to calculate weights per weight, you know how to calculate, and so forth. Yeah. Okay, next one, let's look at another very important topic, which is the pH. Okay, the pH of the solution is very, very important, because the pH can affect a lot of things here. The pH not only will affect the stability of the solution, sometimes it can affect the shelf life as well. Okay, it can affect the shelf life. It can positively affecting or negatively affecting. Okay, like pH, low pH, it can last longer because microbiologically they do not the microorganism doesn't like acidic pH. Okay, but if it's in acidic pH, sometimes some of the molecule may be not may be destabilized, okay, or undergo chemical hydrolysis and so forth. Okay, so there are pros and cons. So the pH of solution is very important. Yeah. When you're looking at the theory, Bronsted theory of acid and base, okay, acid is any hydrogen-containing substance that donates a proton. Okay, in this case, when you're talking about proton, you're talking about hydrogen ions to another substance. Okay, so always remember, acid is donation of proton. Base is when they accept. Okay, so when you form a product, the acid will become a conjugate base. Okay, because it's ready to accept the hydrogen ion, and the base will become a conjugate acid because it can start donating a hydrogen ion. Yeah. So this is very simple. Okay, whenever you can donate, okay, in this case HCl is a strong acid, you donate hydrogen ion. Okay, so it's termed acid. The one that will accept is called base, acid base. Okay, so in donated, what happened? This one, it become what we call conjugate base, because what with the term base, it can accept the hydrogen ion in this case. Yeah, when this one, the base one accepted, become a conjugate acid because now it has additional hydrogen ion that can be donated. Same goes to this one. This one can donate, that's why we call it acid. Okay, hydrogen ion can be donated, is acid. The one that can be accepted is called base. Okay, so we have a conjugate acid. One is being accepted, the hydrogen ion, because now it can donate the hydrogen ion. Whereas this one, once donated, it becomes conjugate base because now you can start accepting the hydrogen ion. Yeah. So again, acid donate hydrogen ion, base accept the hydrogen ion. Okay, I have all Bronsted acid and base. Okay, so from here very simple. In this case, this one will accept, become NH4 plus, so it's a base. This one will become an acid. Okay, so after donated, become conjugate base and conjugated acid. Yeah. So when you're looking at the pH, pH is the most common one that we use. You can become another one is called pOH. Okay, looking at the concentration of the hydroxyl ion, OH. Okay, but that is less common for food, for things, for the normal practices. We usually use pH. Okay, H for the concentration of hydrogen ion. Although commonly we use the pH is equal to negative log of the hydrogen ion concentrations, we can simplify it to hydrogen ion itself. Yeah, not H3O plus. Yeah. Okay. So you can see from here examples from the pH. The low pH, we got all this like lemon juice, okay. The higher pH, we got like milk, okay. In a way, food usually is lower pH, below 7. Okay. Those that is above 7, usually, I not say all, yeah. Usually they are for cleaning purposes. Okay, base is a very good cleaning substance. Yeah. That's why you can see from here, household ammonia, liquid household cleaner, and so forth. Yeah. So using a pH meter, you can use it to measure the pH directly. They tell you the unit over here. Okay. So when got chance, I can go and teach you properly how to use the thermometer, the pH meter. Usually there's a probe over here, and then there's a temperature probe over here to measure. As I mentioned, okay, the temperature can influence or can slightly affect the pH value. Yeah, so make sure when you tells or when you report a certain pH, make sure you tell what temperature you measure the pH at. Okay. Okay. The next one is like we want to talk about acid or base. Okay. Sometimes we talk about strong acid, strong base. What does it mean by strong? Okay. And another word is the weak acid, weak base. What does it mean? Okay. Whether is it strong or weak, it got to do with what we call dissociation. How much the acid will release the hydrogen ion. Okay, how much in terms of acid, yeah? How much if you donate out the hydrogen ion? If you donate little bit, then it's considered as a weak acid. If you donate all or complete, is very strong acid, yeah. So if an acid, okay, you can see from here, this is an acid, okay. So this one after donated become this, okay, become conjugate base. This one is the acid, okay, conjugate acid. So if the acid or base that dissociate almost completely is equal to strong acid, yeah, or base. If the acid or base that dissociate to a much weaker then is called the weak acid and weak base, yeah. So what it means, right, is that this one, if after dissociated, okay, in the solution, if you find that here is 0%, or maybe 1%, okay, 1%. This one 99%. Okay, what does it mean? It's complete, 99% here. It means that it directly donated 99% of the hydrogen ion. So that is strong acid. Okay, that is strong acid. Okay, how you can represent the strength of acid is using what we call the dissociation constant, Ka value. Alright, how you calculate the Ka value? Ka value equal to the concentration of this. This one means the bracket here means concentration, yeah. Okay, by the way. So concentration of this and this divided by the concentration of this. The higher, what happens is that the higher the Ka value, okay, represented by high concentration of this and low concentration of this, is the larger the Ka value means a stronger acid. How you can get the higher Ka value is by having these top two very high value, this one very little, okay, which means that most of these has been converted to these two. Alright. Okay, before I go to that, if it's a low Ka value means what? Low Ka means that this one convert little bit to this one, and usually you will have these two, the value is lower, this one the value is high, then your Ka value will be lower, a lot lower. Okay, so it lower means that it's a weak acid. Okay, so you can look at here. Whoa, the dissociation constant for HCl, all this is almost 100%, very very large, very strong. Whereas you look at this like boric acid, or we call weak acid, you can see mostly is still in this form. Acetic acid is the vinegar. That is why sometimes we can drink vinegar. It won't burn your tongue because it's a weak acid. Most of the thing, even though you drink, is going to be in this form, not in the dissociated form. They didn't release all of the hydrogen ion in this molecule. Most of it you're going to find is this one in your the vinegar. Okay. So water is commonly used as a solvent to prepare solutions. So let's look at the acid and base property of pure water. When you're looking at water, okay, it can behave both as a acid and the base here for water. But the thing is that it only dissociate very little. Most of the time it's going to be in the water molecule form. It's so little, okay, you can use the equations to determine, okay, the concentration of this, and this is very low. It's only 10, the concentration is 1 times 10 to the power of negative 7. This one is the 1 times 10 to the minus 7. It's very little. So we use this as a benchmark of water, as a benchmark to calculate the pH value. Alright, so for water, okay, how we calculate is neutral is when we use this. The Kw, W stands for water, is the concentration of this times this. Okay, so you can see the total concentration is of water is 1 times 10 to the power negative 14. Alright, so the Kw is temperature. So if 40 degrees Celsius, the Kw will be higher. You can see from here. Yeah. Normally 25 at room temperature, the Kw is 1 times 10 to the negative 14 molar, yeah, square. So how this translate to the acid or base? Okay, we use this the Kw, okay, as a benchmark to determine a solution in acid or base. When you have the hydrogen ion, okay, is equal to OH, is what we call neutral. If the hydrogen ion is greater than the OH, is acidic. If this one is greater than the hydrogen ion, is called basic. Yeah. So water, we use it as a benchmark, pH 7. Okay. Because when you have more acidic hydrogen ion, then you're going to go to acidic. If you got more of the hydrogen ion can accept a lot of hydrogen ion, then you're going to be the base side here. Okay, let's practice this here. Classify each of the following solution as acidic, basic, or neutral. Calculate the molar concentration of iron whose concentration is not given here. So if you're looking at this, the hydrogen ion of this is 1 times 10 to the negative 4. Okay, so let's calculate this one first. So is this solution acidic or base? So let's look at this here. If you given this one, the OH value, okay, so is 1 times 10 to the negative 14, okay, divided, because this one is total, yeah. This one times the hydrogen ion, okay, is 1 times 10 to the negative 14, yeah. So since we have this concentration, so will be this divided by the hydrogen ion. So we get 1 times 10, 1 times 1 to the negative 10, yeah. So is this smaller or this one smaller? Of course, this is smaller. Okay, so the concentration value, the OH value is a lot smaller, and hence this is a acidic solution. Okay, so use that to determine acidic or basic. How about the other one? The other one, the B, you look at this. So again, you use by the same formulation. Okay, so in this case, we divided by the OH. Okay, so after divided is 1 times 1 to the negative 5. Alright, so is this concentration greater or the OH greater? In this case, the concentration of this is greater, so is this one is greater, this one is less. So in this acidic solution, yeah. So using all this, right, you can calculate the acidic or basic of the solution. So if you got any question is still not very clear, please ask your questions in the Padlets. Okay, I will try my best to answer you. Okay, so if you got no questions, so make sure you indicate no question in your Padlet. Yeah, so I will end my session over here. Thank you very much.